Hey everyone! Today we will review the paper Unified CNNs and Transformers Underlying Learning Mechanism Reveals Multi-Head Attention Modus Vivendi. A paper by
Ella Koresh, Ronit Gross, Yuval Meir, Yarben Tzach, Tal Halevi, and Ido Kanter.
This paper discusses an explainable approach to how attention mechanisms as well as convolutional layers are capable of learning. We use the compact convolutional transformer architecture, known as CCT, for this research, specifically CCT7, which is comprised of a convolutional and reshape layers, 7 transformer encoder blocks, a sequence pooling layer, and a fully connected layer which connects to the class output layer. The initial convolution and reshape layer receives an image input of shape 32 by 32 in RGB format. The convolutional layer has 256 output channels, and after max pooling the 32 by 32 are turned to 16 by 16, which are later reshaped to 256 as well. This results in a 256 by 256 feature size that will be propagated along the architecture. Since each of the 7 transformer blocks conserves the feature size, it will remain the same until the output layer.
Hey everyone, let's look at a single transformer encoder block. Each block is comprised of a multi-head attention, in short MHA subblock, and a feed-forward subblock, FF. The MHA comprising a multi-head attention layer and a fully connected projection layer, and the feed-forward consisting of 2 fully connected layers, linear 1 and 2. The CCT7 architecture's MHA layer has 4 attention heads. Now, let's take a deeper look into the mechanism underlying this system's learning. We take the pre-trained architecture and cut it at a designated block, specifically block 5 in this example. We then insert a new untrained sequence pooling and fully connected layers, which will connect block 5's output to our now new output layer. After performing the new training phase, we then look at our new fully connected layer to the output. Each node is connected to every other node in the consecutive layer, but in order to assess the functionality of each individual node, we will look at the output generated by a single node to the output layer, by silencing all the other nodes. There are 100 outputs, as in the number of labels in the CIFAR 100 dataset that the model was trained upon. For each input label belonging to one of the 100 labels, we accumulate the fields that the input type generates on the 100 output fields. This results in a matrix of shape 100 by 100, which is then normalized by the maximal matrix value.
Let's take a deeper look at this matrix. Each row represents an input label, and each column an output field for the 100 labels. Each row is the accumulative field generated by all the input images belonging to that input label. In this example, horses. We can see that the accumulative field generates different averaged output field strength for different labels. The diagonal elements designate how well the input was correctly identified by the node. We then take the matrix and apply a threshold to it. The threshold is a number between 0 and 1, since the maximal value is 1, and all elements below the threshold will be zeroed, while all elements above the threshold will be given the value of 1, denoted by white pixels. This helps to distinguish all the valuable or important elements that generate the strongest outputs. Let's take a deeper insight into the matrix we have received. We permute the axes and see that clusters are formed along the diagonal. Clusters are painted white, and outside cluster elements are colored yellow. Clusters are groups of labels that the node recognizes but can't tell apart. Each label within a cluster can be confused, sort of speaking, with the other labels within the cluster by the node. This means that the node doesn't recognize each label by itself, but rather it recognizes small groups of labels with high probability. Using the average number of clusters, cluster size, diagonal, and noise in the nodes of each layer, we can receive a set of quantifiable elements that can help us measure how the system fares. We can also measure the average accuracy of each layer using the newly trained fully connected and sequence pooling layers. After the first transformer encoder block, we get an accuracy of 0.464, but as the layers progress, we see that the accuracy increases, while the average noise usually decreases. Using these features, we can calculate the average signal-to-noise ratio of each layer. By using the following approximation, the signal is approximated by the averaged cluster size times the average number of clusters per nodes multiplied by the number of labels, which is 100 in this scenario. Our noise is the average noise per matrix value, denoted by the letter n, and equals the average outer cluster elements in all the nodes. We see that our signal-to-noise ratio monotonously increases with the layers, growing stronger until the last layer with the highest accuracy and highest SNR. Let's look at the last layer, specifically the distribution of labels among clusters. We count the number of appearances of each label across all the clusters and all nodes, and we see that a clear average number of label appearance emerges with all labels slightly fluctuating around it.
Let's look at how we can apply this knowledge to perform a dilution of the network. This process is known as applied nodal diagonal connection, or ANDC pruning. Before pruning, all nodes are fully connected to all the other nodes in the successive layer. As we assessed earlier, each node recognizes a specific subset of labels, and it is connected to nodes whom also recognize a specific set of labels. Using the ANDC pruning, we can recognize connections between nodes who do not share similar elements and prune them. The logic behind this step is that each node generates a signal only on its label elements, those that appear in its clusters. Therefore, all other connections to nodes who do not share similar label elements can be pruned since they primarily generate noise. This results in a highly pruned network with fewer connections between nodes of different layers. ANDC pruning was performed on the CCT7 architecture for the 7th block. Note that a different threshold was used to deduce the optimal clusters, but it was always around the magnitude of 0.35. For each set of weights, we need the clusters of both the input nodes and its output nodes. On the rightmost column, we can see what's the dilution rate. That is, the fraction of weights that can be diluted using this method. After the dilution is performed, a short training session takes place, and the architecture returns to its optimal accuracy, but now highly diluted. Let's look at the layers and see the dilution of each layer. The result is a total dilution of around 80% and a massive reduction in parameters from 524,000 to 93,000.
Now let's delve deeper into the main novelty of this paper, and that's the modus vivendi, or cooperation, among filter heads to achieve optimal learning. We mentioned that our architecture is comprised of a convolutional and a reshape layer, 7 transformer encoder blocks, and a sequence pool and fully connected layer which lead to the outputs. Let's look at the last attention block. We have 4 fully connected layers in our block: a QKV layer that creates our attention heads, a projection layer after the sealed dot product attention, and the 2 linear layers of the feed-forward subblock. If we cut our subblock right before the projection layer, what we will receive is the attention heads post the sealed dot product. Let's take a closer look at our attention heads. In this architecture, we have 4, although that number can theoretically change. We'll designate a color to each head. We now add a sequence pooling and fully connected layer to the class output that will receive the outputs of the sealed dot product attention. We will now train this newly added layers to reach minimal loss while maintaining the other layers fixed. in a similar process that we've done beforehand at the end of the blocks. Each head is comprised of 64 nodes, a total of 256 from all the heads put together. And each one of these nodes generates its own label element matrix. Let's now look at the accumulative appearance of each label in the clusters of each head and see if we notice a pattern. The first head has some labels that appear quite a lot in its clusters, some rarely, and some don't appear at all. The second head has a similar distribution of label appearances, but for different labels. A similar pattern appears with the third and fourth heads as well. If we take all the labels that appeared at least more than twice than any other label in each head, a pattern emerges. We see that for head 1, we have 23 labels that appear at least twice more than in any of the other heads. Furthermore, if we measure the accuracy by silencing all heads except one, we see that head 1 has the highest accuracy for those specified labels. We will call those labels head 1 labels. We then repeat the process for the other heads. A similar pattern emerges for the rest of the 3 heads as well, meaning that this isn't just a fluctuation, but rather that the system designates, sort of speaking, a quarter of the labels to each one of the 4 heads. When all the heads are put together, each one generates a strong signal on its labels and a weaker signal on all other labels, thus creating the system's modus vivendi. One can think of this as a symmetry breaking, where each head now recognizes a subset of labels instead of trying to recognize all the labels together. To better understand the effectiveness of the mechanism, let's look at a rather interesting phenomenon that occurs pertaining the information of the labels themselves. CFAR 100 has 100 labels that are divided into 20 groups of 5. Every 5 labels belong to a course label that indicate a category group, such as dogs, cats, and hamsters belonging to the category of pets, and forks, knives, and spoons belonging to utensils. When we look at the labels belonging to a specific head, we see that an attempt at grouping labels together from the same course label is made by the head. For head 1, we see that 2 entire course labels are within the head's labels, meaning that 2 entire groups of 5 labels from the same course labels have been chosen. We also see a rather high tendency for the head to choose a rather large part of the course label, that is 4 out of 5 labels or 3 out of 5. Overall, we see that the vast majority of labels in each head are grouped together with other labels of their course label group. Now let's ask ourselves, what's the probability of that happening by random? We ran tens of thousands of simulations where every time 25, 20, 15, 10, and 5 labels were randomly picked. We then averaged the appearance of the number of labels out of the course label appearance to see what's the chance, or distribution, of having an entire or part of a course label. We see that the number of times an entire course label was chosen was slim, and that a clear vast majority to 1 and 2 labels from a course label are the most common random occurrence. Choosing 3 out of 5 labels is rare, although not non-existent, and choosing 4 or more is very rare indeed. This is a clear indication that the attention heads actively choose labels from similar groups, since a random occurrence is very unlikely to create such distributions. When we go lower in the blocks, we see that the distribution towards entire course labels is scarcer, but also that the majority of labels are not part of any label heads. We do see that for head 2 in block 6, which is the only head with more than 20 labels, that there is a stronger inclination to have more labels from similar course labels, indicating that this head is attempting to orient itself according to the mechanism, even though the entire system is not there yet, but will only reach so in the 7th block. We mentioned the symmetry breaking before, but as we mentioned earlier, the labels belonging to a specific head depend on arbitrary choice of having each label appear at least twice more than in the other heads. Let's take a deeper look at that threshold and see what happens to the symmetry breaking for different thresholds. We see that when the appearance ratio is 1, almost all labels undergo a symmetry breaking since the threshold is too low. As the threshold ratio increases, Block 7 retains most of its breaking components, but lower blocks have a lesser amount of labels that undergo symmetry breaking, indicating that it is stronger at higher levels than lower levels and more robust to the ratio that we choose. We also see a turning point at the threshold ratio of 2, indicating this was an appropriate decision. Lastly, we checked how labels who undergo breaking fare in comparison to labels who do not. We took all the labels that underwent symmetry breaking in Block 7 and compared what was their accuracy for the entire trained system, or before performing any cuts. We see that labels that underwent symmetry breaking had a clear higher accuracy than labels who did not. It is important to note that symmetry breaking does not occur at lower layers, but only at higher layers. After a certain critical layer, LC, the phenomenon of symmetry breaking emerges, where each head attempts to recognize a subset of labels. This is similar to physical systems that, after a critical temperature turn, undergo a phase transition, like how cooling water turns to ice or how magnetism is achieved after cooling below a critical temperature. We hope you enjoyed our explanation and that you learned a bit more on how the wonderful world of machine learning works. For more information, check out our paper.